Welcome to the Deep Dive, where we take that stack of dense research and cut straight to the core insights you need to know.
Today, we're definitely moving past the digital world of chatbots like ChatGPT.
Way past it.
We're talking about AI that can actually, move,
Kind of-
interact, survive out here in the physical world.
And that's the big question, isn't it? Are these incredibly smart, large language models we have now actually smart enough to deal with, well, reality, physics?
That's the core tension, yeah. All the research we looked at circles around this. So today's deep dive is all about embodied artificial intelligence, EAI.
Right, EAI. And specifically, how the reasoning power of these newer multimodal large language models, MLLMs,
The ones that handle more than just text.
exactly, how that's merging with something called world models, which seem to handle the physics side.
It's a crucial fusion. And when we talk about MLLMs, it's important to remember that distinction. Traditional AI, it's disembodied.
It lives purely online, solving abstract problems.
Precisely. MLLMs are the bridge. They start pulling in real-world senses, vision, touch, sound alongside the language.
Okay, so that's the step towards genuine embodied AI.
Mm.
Agents that can see, reason about, and actually do things in the physical world.
It's a whole different paradigm. Intelligence isn't just calculating inside a chip. It really emerges from that constant loop of sensing, thinking, and acting.
You sense the world, you figure out what it means, you act, and that changes what you sense next.
And, this isn't some brand new concept that just popped up. No, the sources we read trace the theoretical roots way back. Alan Turing, 1950.
Turing himself.
Really?
Yeah. He talked about needing physical experience for genuine intelligence, called it the embodied Turing test.
Wow. So the ultimate goal here, what researchers are aiming for with this next generation AI, it's about bridging that gap.
That's it. The gap between the, let's say, abstract brilliance of language models and the hard, messy rules of physical reality.
Okay, so if you want an AI that can, load your dishwasher or navigate a tricky warehouse, or even a disaster zone.
Right. It needs a solid foundation.
Yeah.
The sources talk about a kind of operating system for EAI, a three-part loop.
Yeah, a closed loop system. It's essential. It's how the agent constantly learns and adapts to what's happening.
Okay, let's unpack that loop, because that sounds fundamental. Where does it start?
It kicks off with active perception. And the key word there is active.
Meaning?
Meaning it's not just passively soaking up data like a security camera. It's using its sensors cameras, maybe LiDAR, touch sensors, to selectively gather the information it needs for whatever task it's doing.
Okay, so if I tell it find my keys, active perception means it's smart enough to focus its eyes on the floor and tables, not like the ceiling fan.
Exactly right. It figures out what's relevant. Then that relevant data feeds into the next stage, embodied cognition.
The thinking part.
Sort of. It's the agent's internal mind, yeah. This is where its past experiences, its internal map of the world, maybe even some self-reflection come in. It processes the sensory input and decides, okay, based on this, what's the next sensible action?
And that decision leads to the final part of the loop.
Dynamic interaction. This is where the robot or agent actually does something. It uses its motors, its actuators, to move, to grasp an object, to navigate.
And by acting, it changes the environment.
Which immediately creates new sensory data.
Which kicks off active perception again. The loop closes.
Precisely. It's a continuous cycle. But there's one more piece the sources really hammer home.
That's that.
Hardware embodiment, doing all this sensing and thinking and acting in real time in the messy physical world, it takes serious hardware.
Right, you can't just run this on a standard laptop.
Not effectively. You need specialized chips, low latency connections, power efficiency, things that can handle the demands outside a nice, cool data center.
Makes sense. Now, thinking about how EAI developed, the research mentioned moving away from early approaches that used to be unimodal.
Yeah, meaning they focus heavily on just one type of input. Maybe an agent was brilliant with vision or another was great with language commands, but they couldn't really integrate different senses.
And why was that a dead end?
Just too limited, too narrow. Imagine trying to figure out if a glass is delicate using only your eyes. You have no sense of touch, no force feedback, you'd likely break things.
Okay, so relying on just vision or just language meant they couldn't handle complex, ambiguous situations where you need multiple clues.
Exactly. Which brings us to where we are now, the shift to multimodal EAI. integrating vision, sound, touch, language. That's what gives you robustness and flexibility.
And that convergence is really powered by these two key technologies we mentioned earlier.
The two pillars, MLLMs and world models.
Okay, let's dig into pillar one.
Yeah.
Multimodal large language models, MLLMs first. We know LLMs are great with text. What happens when you make them multimodal for EAI? What's their superpower?
They essentially become the semantic brain of the operation. Their strength is in high-level reasoning and, crucially, task decomposition.
Breaking down big goals.
Exactly. You can give it a vague instruction like, tidy up the break room.
Which involves a lot of steps.
Right. And the MLLM can translate that into a sequence of more concrete actions. Locate sponge, pick up sponge, find dirty counter, wipe counter. It understands the meaning and the steps involved, expressed in natural language.
That's impressive, but it's still abstract planning, isn't it? How do you stop the MLLM from suggesting something like, okay, phase one, levitate the coffee cups to the sink? How do you ground it?
Yeah, exactly. You need constraints. And the research points to frameworks like SayCan as a good example.
SayCan. How does that work?
It basically forces the MLLM to play within the rules. It can only suggest actions from a pre-approved action library, things the specific robot body is known to be capable of doing.
So it knows the robot can grasp but not levitate.
Precisely. And then it uses something called value functions to double-check if that sequence of allowed actions is actually likely to succeed in the current physical state of the world. Is the path clear? Is the object reachable?
So it's thinking, but it's also constantly checking. Can I realistically do this right now? Okay, that makes sense. But even with these checks, what's the fundamental weakness if you only have an MLLM running the show?
The core limitation is that its intelligence is still fundamentally semantic, abstract. It's amazing at context and language, but it often overlooks or misunderstands subtle physical constraints.
Like what?
Like, it might plan a path for an arm that ignores friction on a specific surface, or it might understand the concept grasp the bottle, but not intuitively grasp that a half-full open bottle needs to be kept upright due to gravity. It doesn't feel the physics.
It knows the word gravity, but doesn't have the built-in intuition.
Okay.
And that lack of physical intuition is exactly where the second pillar comes in.
Right. Pillar 2. World models, WMs. These are the physics engines.
The simulators.
Exactly. They give the agent that missing physical intuition. They do this in two main ways. First, they build internal representations.
Like a mental map.
Kind of, but more dynamic. It's a latent map capturing how objects behave, the basic laws of physics like gravity, and the spatial layout of the environment. It's the agent's internal understanding of what's where and how stuff works.
Okay, so it builds this internal physics simulation. What's the second thing?
Future prediction. This is key. Based on that internal representation, the WM can simulate what's likely to happen next if the agent takes a certain action.
Running what-if scenarios.
Exactly. Across different timescales, too. Short term, if I move my arm this way while I knock over that vase, and maybe longer term, if I take this route while I run out of battery before reaching the goal. It helps preempt mistakes and risky moves.
So the MLLM might propose, let's quickly grab that glass near the edge.
And the world model instantly runs a simulation and flags it. Hold on, physics predicts that's unstable, high chance of falling. It's that internal reality check.
Okay, that sounds incredibly useful. But world models must have their own blind spots, right?
Yeah.
If MLMs lack physics, what do WMs lack?
They have the mirror image problem, essentially. WMs are brilliant at physics-aware simulation and prediction for known dynamics, but they really struggle with open-ended semantic reasoning.
What does that mean in practice?
They don't generalize well to new abstract tasks without being explicitly programmed or trained for them. A WM might be perfectly simulated to know how to pick up a specific type of block.
It knows the physics of grasping block A.
Right, but if you give it a high-level command like, clean up this mess involving different objects, maybe liquids, maybe sorting. The WM alone doesn't understand the general goal or how to break it down. It lacks that MLLM-style task decomposition ability.
It knows the how of specific physical actions, but not the what or why of a general task.
You got it. And that's why neither pillar alone is sufficient. You absolutely need to fuse them.
The MLLM provides the high-level plan, the semantic understanding. The WM provides the how, the grounded physics-aware execution and simulation.
Exactly. The joint MLM-WM architecture is where the magic happens. It bridges semantic intelligence with physical reality.
And the sources said they actually boost each other. It's not just patching weaknesses.
Oh yeah, there's real synergy. They actively enhance each other's capabilities.
Okay, how does the world model help the MLLM specifically?
Well, the WM provides that crucial real-time physics check. It constrains the MLLM's sometimes overly creative plans with the hard rules of gravity, friction, object permanence. It basically stops the MLLM from suggesting physically stupid things.
It keeps the abstract thinker grounded.
Mm-hmm. And then flipping it around.
How does the MLLM boost the world model?
The MLLM brings its power of semantic understanding and data fusion. It can take all the messy multimodal input, the video feed, the sounds, the tactile feedback, maybe even text descriptions, and fuse it into a unified high-level understanding of the situation.
Which the WM can then use.
Right. It enriches the WM's representation of the world. Plus, the MLLM's task decomposition ability gives the WM the structure it needs. The MLLM breaks down Clean the Kitchen into steps the WM can simulate and execute safely.
Okay, so that combination allows for much more complex long-term tasks. The sources mentioned an example, Evo Agent.
That's right. Evo Agent is a good illustration of this joint approach in action. It's designed for autonomous evolution, tackling long horizon tasks.
Meaning it learns and adapts over time.
Yeah, through continuous self-planning, that's the MLLM part, self-reflection, evaluating its actions, and self-control, using the WM for execution, it constantly updates its understanding and performance without a human needing to step in for every little correction.
That sounds powerful. But trying to get these two systems, the slow, thoughtful MLLM and the fast, reactive WM, to work together smoothly must be tricky. What are the big roadblocks researchers are hitting?
The research highlights a couple of major challenges. First one is pretty intuitive, real-time synchronization latency.
The speed mismatch.
Exactly. MLLMs can take a bit of time to process complex semantic information. World models, especially for physics, need to run really fast to be useful in dynamic situations. If there's a lag.
The robot reacts too late. It crashes or misses the object.
Right. Getting that timing right, especially as tasks get more complex, is a huge engineering challenge.
Okay, latency. What's the second big hurdle?
Semantic physical misalignment. This is a bit more subtle.
Meaning?
It's when the MLLM makes a plan that seems logical semantically, but it violates some physical rule that the world model hasn't actually learned or simulated perfectly yet.
So the WM might know about friction generally, but maybe not the specific friction of, say, an icy patch versus wet grass.
Precisely. The MLLM says go there, which seems fine, but the WM simulation is incomplete for that specific scenario, leading to an unexpected slip or failure. The high-level plan fails because of unmodeled physics detail.
Okay, those are significant challenges. But assuming researchers make progress, let's zoom out. Why should you, our listener, care about this MLLM-WM fusion? What does it unlock in the real world?
Oh, the applications are already starting to roll out, and they're pretty transformative. Think about surface robotics.
Robots in homes, hospitals, stores?
Yeah. Systems like Google's RT2 or that SeiCan framework we mentioned, they're moving way beyond simple, pre-programmed automation. They can handle complex instructions given in natural language.
Like, could you clear the table and stack the blue plates by the sink?
Exactly. Things that require understanding context, object properties, and multiple steps. That kind of high-level reasoning in physical tasks just wasn't possible before this fusion.
And I imagine this impacts factories, too. Industrial robotics.
Massively. Industrial robots are becoming much less, well, dumb.
Less repetitive, more adaptive.
Exactly. They're using multiple sensors, LiDAR for distance, thermal for heat, regular cameras to build up a much richer understanding of their workspace.
So instead of just stopping when something unexpected is in the way.
They can actually understand what it is, maybe predict its movement, and find a safe way around it. Or they can adjust their grip strength on the fly based on sensor feedback if they realize an object is more fragile than expected.
The sources mentioned examples like fixing parts at Tesla or sorting packages.
Yeah, huge warehouses like JD's or T-Malls are using robots with this kind of embodied intelligence for complex sorting and handling, adapting to different shapes, sizes, and materials.
Okay, service robots, industrial robots. What about higher stakes applications? The sources mentioned rescue UAVs, drones.
This is a really compelling area. We're shifting from drones that are basically remote-controlled cameras to truly embodied agents.
Drones that can think for themselves.
To a degree, yes. They can perceive the environment in detail, understand complex voice commands like search the area near the collapsed bridge, look for signs of life.
And the world model helps them stay safe.
Critically, it allows them to simulate potentially dangerous environments before flying into them. Is that building likely to collapse further? Is there a risk of gas leaks? The WM helps plan safer routes, especially in places where GPS might be unreliable or denied.
Wow. Okay, so across the board, this fusion enables more autonomy, more flexibility, more intelligence in the physical world. Where does the research go next? What's the long-term vision?
A big focus is on autonomous EAI, really pushing for long-term independence. Agents that don't just perform tasks but learn continuously, adapt their perception, and refine their internal world models over weeks or months, not just hours.
Getting closer to true lifelong learning.
Exactly. Another major direction is moving beyond single agents.
Ah, like robot teams.
Yep, swarm EAI. The idea is creating collective intelligence. Multiple agents coordinating, sharing sensor data, maybe even contributing to a shared, collaborative world model of the environment.
Imagine a team of rescue robots mapping a disaster site together.
Precisely. Much more efficient and robust than a single agent. And finally, perhaps the most crucial direction for real-world deployment.
Let me guess. Safety and reliability.
Trustworthiness, EAI, absolutely. As these agents become more capable and operate in sensitive areas, homes, hospitals, rescue sites, we need guarantees.
Guarantees about what?
Verifiable safety, explainability, why did the robot do that, and adherence to ethical guidelines. We need to be able to trust these systems implicitly, especially when things go wrong.
That makes total sense. So wrapping this up, the core takeaway seems crystal clear. If we want artificial general intelligence, AGI, that can actually function effectively outside the digital realm,
In our messy physical world.
then this dynamic fusion, this partnership between the semantic reasoning of MLLMs and the physics-aware simulation of world models seems absolutely fundamental.
It really feels like the key. We're watching AI step off the screen and into the world.
And that brings us to our final thought for you to ponder. As these embodied agents get more autonomous, more capable of long-term planning and even self-reflection, how do we tackle the really hard part?
The ethical dimension.
Exactly.
Yeah.
Especially in high-stakes situations like rescue or healthcare. How do we ensure these increasingly complex systems operating in novel situations their world models might not fully capture learn to not just follow rules, but to actually identify subtle moral hazards and adhere strictly to human values? How do we build a moral compass into the machine?